Okay, this is the last problem set for the unit, at least in this section, and I'm going to answer similar problems that we've seen in problem sets 1 and 2, except for the last problem I plan to do in this video is to order a bunch of anions, to order a bunch of molecules, they don't necessarily have to be anions, in order of decreasing base strength. So the strongest base will be listed first, or be given number 1, going down to the least basic. Alright. This is problem set 3. The previous two problem sets, 1 and 2, were under these two videos here. 08G30, what's going on? There we go. And 08G3-5. Okay. And I pre-wrote these problems, and the first one is these three. Draw elimination products, pick the major product, and then just state the mechanism. We're not going to draw any mechanisms, I don't think, in this problem set. Okay. Go ahead and pause the video, try to answer this problem. Well, first copy the problem, and then try to answer them with the video paused. Alright, how would I do this problem? The way that I would do this problem is make a couple notes. Here we have a weak base. They do want us to draw elimination products, so I'm not going to worry about substitution. Don't worry about the heat, it just speeds up the reaction. We have a tertiary alkyl halide, and again, it doesn't really matter if it's primary, secondary, or tertiary. It just matters whether I have a strong or weak base. But I do want to label the alpha and the beta carbons. And when I draw the products, I want to keep in mind, is there any possible cis-trans isomerism? I'm going to make the double bond to the left first. Okay. Then I'll make the double bond to the top carbon. And I'll realize that that double bond up here is the same thing as putting the double bond over here because of rotation of the bond, and therefore I don't have to draw a new compound to show the elimination of this beta hydrogen. Neither of these have cis or trans. The major product is going to be this, tri-substituted versus di-substituted. And the mechanism for both of these is E1. Why E1? Because we have a weak base, and the base is going to wait until the leaving group pops off on its own. Why E1? You know that unimolecular goes to carbocation, and oh no, we should not even talk about that. We're not concerned about whether this is primary, secondary, or tertiary. That's a big concern for substitution reactions. But for elimination reactions, look at the base. Weak base, it has to hang out until the halide pops off. Has to. If it's a strong base, the strong base will immediately deprotonate or strip off a proton to form the double bond and kick out the leaving group. For instance, this is a strong base. Now, how would I draw this? You could draw it like this, NaOET, right? Or NaO with a ethyl group. Ethanol looks like this. Okay. So they're very similar, but you're going to use this top molecule as the base, and it's a strong base. I'm using this molecule as a base not because it's written on top. I'm using this as the base because it's a stronger base than ethanol. So when you're giving both of these, you go with the one that's stronger, and then that will determine whether you're doing E1 or E2. alpha, beta, ooh. Oh, I'm glad I have this problem. Because we have 2 beta carbons. The strategy is to make a double bond between the alpha and the beta. There you have that. But look what happens if I'm not thinking through this very clearly. I'm going to put a double bond to the right. You see the problem now? I do have 3 methyl groups, 1, 2, 3, so I have to draw those 3 methyl groups, 1, 2, and 3. But do you see how it's ridiculous to put a double bond here? That's a 5-bonded carbon. You can't put a double bond here because there's no beta hydrogen. So here there's no beta H. It is a beta carbon, but there is no beta hydrogen. So this is not a product. Okay. And there's one product. It's the major product. It has to be this one. Since you're using a strong base, you are automatically E2. Next one. Same. Strong base. We only have 1 beta carbon. Mark the alpha. Anything next to the alpha is a beta. And we only have 1 product again. It's this one here. You could circle it, or you don't have to. It should be clear to the grader that you only drew 1 product, and that's a major product. So those are your answers for those 3 problems. I have a slightly different problem than what we've seen so far in set 1 and 2 for the next one here. How would you make the following alkene? So we know that we can make an alkene from an alkyl halide. See, the problem isn't even giving you that clue. You should know that by now. To make an alkene, we start from an alkyl halide, and we do an elimination. One possibility, and maybe the only possibility, is this. Again, for me, it's trial and error. So I'm going to pretend, well, if I have this halide, okay, can I get this product here? I'm going to use a base. The base that I typically like to use is NaOET. You could use NaOH, you could use NH2-, just a really strong base. Should work. And my product is this. Let me mark it up. Alpha, beta. Oh, man, it's this one up here. I didn't realize that. Okay. But there's actually another way to do this. Let's put the halide on the tertiary carbon. When the problem asks, can you do a synthesis or can you make a product, the implication is, or the unwritten rule is, that you want to propose a synthesis or propose a reaction where that product is at least the major product, if not the only product. But it's acceptable to draw a reaction where it's the major product. If you draw a reaction where this is the minor product, there will be some point deductions, because this is implying that you want to make it as efficiently as possible. Okay. And if it's a major product, I will consider that as efficient. The thing is, if I use NaOET, my major product is going to be the double bond that's in the ring, because it's more substituted than if the double bond was outside of the ring. So I can't use something like NaOET for this, because the major product would have been within the ring. I'm going to draw that here because I know what I am going to do, and I'm going to show the product that I don't want. That. Okay, that's what I don't want. And again, if I use NaOET, that's the product that's going to be major. But there's another alkene that's possible, and it's the one that I actually do want, by making a double bond to the beta carbon on the right. But how do I make this the major product? What is a trick? The trick is to use a bulky base. KOTBU, and then that makes this the major product. We're making the Hoffman product because this is a bulky base, and we've discussed that many times in the previous two problem sets. And for a very crowded base, the size now is the main determinant, and we can't get close enough to a secondary carbon, or at least we can't get as close as we can to a primary carbon. It's easier for this base to strip off the hydrogen here. Now that's true if we use NaOET, but when the base is small, like NaOET, it's not the size that is the determinant, it's the stability. So this would normally be the major product, not because of accessibility, but because it is the more stable product, and typically the major product is the most stable. For a lot of people that's intuitive. It makes sense that the major product is the most stable product. But here, the major product is actually the less stable alkene, and we made the Hoffman product. I know we get a mixture, but this is still the major, and it's still acceptable when you have a question like this. How would you make the following whatever? If it's a major product, you're good. So there are two acceptable answers. Two acceptable answers. Okay. All right, last one. This is different than what we've seen in problem set 1 and 2. Since we're working with base, okay, when we do elimination of an alkyl halide, it would be nice if we can understand or review how to analyze base strength. It's very similar to analyzing acid strength, actually. But what do I want to say about this? This is a review of acid-base reactions. And where am I going to put this? I don't know what unit that was. I think that was unit maybe 4? Yeah, unit 4, I think. But why are we doing it here? Because, again, your elimination reactions have to use a base. And you did want to know, or you do want to make a list of what are the strong bases and what are the weak bases. Now, typically, anions are the strong bases, and neutral are the weak bases. But there are some depictions of molecules that are a little bit confusing. In particularly this guy right here. Okay. What do we have to do to figure out which is the strongest base? Do you remember the phrase, the stronger the acid, the weaker the conjugate base? So the opposite works too. The stronger the base, the weaker the conjugate acid. I have to draw the conjugate acids, because to be able to analyze the bases. I know it's a pain, but if this is a base, it grabs a hydrogen or a proton, and it becomes the conjugate acid. If I could order the conjugate acids, the weaker acid results in the stronger base, and vice versa. The stronger base gives me a weaker conjugate acid. If you want to think about it, let's say this one is the strongest. If this is the strongest base, it wants to become the conjugate acid, and it wants to stay there. If it wants to stay there, then it's not going to want to give up a proton to go back. It's stable, and it's very unreactive. If this is super reactive up here, it will go to the product which has to be less reactive. or else it would go backwards. Okay, so that's another way to think about it. The stronger the base, the weaker the conjugate acid. So I'm drawing all the conjugate acids, and I'm going to find the pKa's for these conjugate acids. And whichever has the weakest acidity or the largest pKa, that means that that acid is very weak. Weak acids lose their hydrogen to give us very strong bases. Okay. Let me say that again. The weaker the acid, the stronger the conjugate base, right? So here's a tricky one. Remember how I've been saying that if you're bonded to a sodium Na+, lithium Li+, or potassium K+, you want to think of it as ionic. So I did draw this as a covalent bond, and there's some textbooks that do that. But when you dissolve this, you got to think of this as an anionic. So where would I put this? Let me put it above it. You want to think of it as this, actually. CH2 minus plus Li. How did I know it was minus? Because Li is positive, and if it's ionic, a salt, it could definitely separate into its two ions. How did I know this was two hydrogens? See, there literally are two hydrogens here, but also Li is plus, so the counterion has to be negative. How do we draw a negative carbon? It's a carbon with 3 bonds and 1 lone pair. If you do the formal charge equation, you'll realize that this is negative when you have this lone pair here. Just like here. See, 3 bonds, 1 lone pair, negative. Now what is the conjugate acid here? Okay. I challenge you to draw me the conjugate acid. How do we draw the conjugate acids for these? You added a proton. Add a proton right there. I know it looks strange. That's your conjugate acid. That's your conjugate acid. NH2 becomes NH3. Acetate becomes acetic acid. Oh, this one's weird. It's not an anion. So what is this going to do? It's going to pick up a proton, because I'm going to pretend this is a base, and its conjugate acid is this. Protonated alcohol. Okay. Now, you could memorize the PKAs, you could look them up in a textbook, or you could rationalize which one is, the most acidic, which one is the least acidic, okay, based on your trends. Remember your trends, they are electronegativity, size, resonance, and hybridization. There's actually one more, a fifth one, that I may or may not have mentioned, and that's induction. But let's not worry about that. I have the pKa's memorized for these, and some of these you should know, like alcohols have a pKa around 15.5. What else can you pick up? Can you beat me? Can you beat me and fill in the rest of these? I'll shut up. Let's race. Okay, I've done with the PKAs. Alright, these are acceptable. This one sometimes I forget, but I know it's negative, and it's around -2. Look what I'm going to label. You know that the higher the pKa, the weaker the acid. So this is the weakest acid. What's the strongest acid? This is the strongest. Let's start with that. The strongest acid. The stronger the acid, the weaker the conjugate base. So I know I labeled this as the conjugate acid, but let's pretend we're going backwards. It doesn't matter what you think is the what do you think is the conjugate. This is a conjugate of that, and that is a conjugate of this, right? So the stronger the acid, the weaker the conjugate base. This is the weakest base because it came from the strongest acid. Let me zoom out a little bit, actually. Yikes. So weakest base. 1, 2, 3, 4, 5, 6. This is number 6. Let's go the opposite way. Let's go for the strongest acid, the strongest base. This is the strongest base. Tricky. It's tricky because you don't initially see the anion. But you have to know that because you have a metal here, you're going to treat it like a salt and you're going to separate. Number 1. This is a popular base. This is called N-butyl lithium. All one word, no space. N stands for normal, meaning that you have the butyl, the 4 carbons in a row. It's not isobutyl, it's not sec-butyl, it's normal butyl, 4 in a row. That's a super strong base, and you'll see that a lot in organic too. You may actually even see it in the next unit, unit 9. Well, what's next? This one's next, so this is number 2. Yeah, I remember using this as one of the bases, strong bases, in an E2 mechanism. E2 mechanism. Next is, that. Number 3. This is also a strong base. It's a carbon anion, but now it's a triple bond, so it's a little less basic than this, but still is a strong base. What am I saying? Right now, 1, 2, and 3, you can use those. You can use those as a strong base. You could use it as, because they're still stronger than O-. Because look at the O- there. That's number 4, right? 1, 2, 3, 4. It's number 4. So anything more basic than this, you can use to do an E2 mechanism. Now you wouldn't want to do an E2 mechanism using this base, number 5. Okay, I know it's O-, and I said oxides are very strong bases. Technically, this is not an oxide because of resonance. That negative charge is bouncing, or actually shared between these 2 oxygens. So that negative charge is not localized. When we have a localized charge, we know that it's unstable, right? So to get rid of that charge, you want to pick up a proton to become neutral. That's the motivation for this oxygen, to become neutral. This has less of a motivation to be a base because it is fairly stable due to resonance. So that's another way to do that if you did not memorize the PKAs. Okay, try to rationalize which one is happy the way it is and which one is not. Whoever's not happy is very reactive and wants to get to a place where they are happier. Neutral. Okay, neutral. Alright. The take-home lesson here is, if I have something like this, let's see if we know how to draw the products here, like that. And I'm going to use a strong base. And a base that typically you don't see used, and it's this one. Okay. Or how could you have seen this? Or you might see it like this with a counter ion. I'll use sodium. Okay. It should be automatic. Whenever you see sodium, lithium, or potassium, separate it and make that atom next to it an anion. This is still a base, okay? It's still going to act like a base. It's a fancy base, but it's still going to act like a base. I could hear someone ask, is this a bulky base? No, because it's linear. So there's not a lot of crowding around this anion. So this is not bulky. So we don't have to worry about picking the Hoffman product as the major product. So this is not bulky. There's only one bulky base that I typically teach, and that's potassium tert butoxide. That's the only bulky base that I typically teach. Some semesters I would teach others, but mostly it's just potassium tert butoxide. Look at the beta carbons. Beta, ooh, beta, beta. But because of symmetry, making a double bond here, yes, would be the same as making the double bond down here. So let me draw that product. The double bond within the ring first. Okay. Again, the double bond here would be identical to the molecule if the double bond was down here. All I have to do is rotate it. Plus, let's take care of the beta carbon on the left. There. Alright, last thing. Do you know which one is the major alkene? It's not a bulky base, so we're just going with our normal Zaitsev rule. Zaitsev said the more stable alkene is the major product. Both of them are pretty stable actually, but this one is more because it's tetra substituted. Do you know how I count? Put 2 dots on the double bond carbons, and count how many groups are attached. A hydrogen I do not consider a group. So if I count what's attached to this dot, I have 1, 2, and then here we have a third group, and we have the fourth position being hydrogen. So this is tri-substituted. One of the groups is a hydrogen. But you notice that here there are no hydrogens. So they're all taken up via carbon, all these bonding sites. We have 4 carbons around the carbon-carbon double bond. 1, 2, 3, 4. Okay. So this is a Zaitsev product, or Zaitsev said this is the major product. You can call it either one, the Zaitsev product or the major product. I think that's it for very straightforward alkyl halide elimination problems. Alright, good luck studying. If you have any questions, let me know. Test yourself. You could always go back through the videos and pause the videos before I show the answer.